Now that we've spent a couple of lessons talking about parallel lines and angles, we're going to take some time to look at parallel and perpendicular lines and the theorems involving them. So let's begin here with Theorem 3.8. 3.8 and 3.9 don't really have formal names that I'm aware of, but I call 3.8 the Transitive Parallel Lines Theorem. And it states, if two lines are parallel to the same line, then they're parallel to each other. In other words, if I'm working in a system and I know that A is parallel to B and B is parallel to C, well, since both A and B are A and C are parallel to the same item, then A must be parallel to C. That's all that this one states. We'll take a look at what this means in the included picture. But first, let's take a look at Theorem 3.9. Parallel perpendicular lines theorem is what I call it. And it states, in a plane, if two lines are perpendicular to the same line, then they're parallel to each other. So now, what do these look like in the diagram that is provided here? This is a a picture of Golden Gate Bridge in San Francisco, and Theorem 3.9, the parallel and perpendicular lines, the tower on the right is perpendicular to the span. Well, the tower on the left is also perpendicular to the span. Since both of them are perpendicular to the span, then we could conclude that the left tower and the right tower are parallel to one another. This is how this works. Now, the transitive parallel lines theorem, if we were to go and take a look at these items again and look at things more broken down inside of the bridge, if we were to take the far side of the left tower, the part closest to here, and the near side of the far tower, they are parallel to each other. Well, the near side of the left tower and the near side of the right tower are parallel to each other. So then that means that the far side of this tower, which if we were to put it into a closer proximity of where it actually is, here, and the near side of the right tower would be parallel to one another. That is the transitive parallel lines theorem. You see these a lot in construction and building items. It helps to be able to do this. You don't have to necessarily measure parallel for all items. If you just know they're parallel to one another or perpendicular to a common item, then you can conclude parallel relationship exists. Now, let's take a look at some perpendicular items. So let's look at this theorem, which is called the perpendicular transversal theorem, states, in a plane, if a line is perpendicular to one of two parallel lines, then it is perpendicular to the other. And the reason we have to say that this exists in a plane is because in a three-dimensional figure, such as a simple cube, if we were to take this edge and say they're perpendicular to each other, but this top one is also perpendicular to this top right side edge, we can't conclude that this edge and that edge are parallel to one another when in fact they're askew. The reason that happens is because they're in different planes. Now, working in a specific plane, the map shown here is a section of downtown Denver, Colorado, and we have a lot of parallel and perpendicular lines in here. If we were to take Champa Street, which is located here, and say that it is perpendicular to 18th Street, but we know that 18th is parallel to 15th, then we can conclude, based on Theorem 310, that Champa is perpendicular to 15th as well. Because it's perpendicular to 18th, we know it's perpendicular to 15th. When city engineers go and design the layout of different neighborhoods, they use this to help establish continuity and the ease and availability of being able to find locations. So with these parallel and perpendicular lines, we have a lot of applications into construction and into city design and layout, and are very useful. So make sure you have these theorems down, ready to use them, and we'll be able to apply them moving forward.